So now what we're going to do is we're going to turn what we know about linear equations and apply it in an accelerated way. So this is kind of the accelerated aspect of after reviewing this material that you covered in 8th grade. During an intense Pokemon Go session, Mr. Kaufman had 46 Pidgeys in his inventory after 2 hours of playing and 79 Pidgeys after 5 hours of playing. Write a function, f of t, that models the number of Pidgeys as a function of time. Use your function to predict when Mr. Kaufman will have 300 Pidgeys in his inventory. So when we're looking at word problems, we're trying to grab numbers and equations and information in order to turn it into an algebraic way. So your first thought here is you need to prepare for your problem. Always, always, always with word problems, we need to prepare first. A preparation can look like many things. We can write down formulas. So for instance, it says that we want to write a function that models the number of Pidgeys as a function of time. It doesn't tell us that it's linear, but it is. So we're going to write down one of our linear modes or forms here at the beginning, because we know that we tend to start with this as our linear equation. We've also been given some numbers, and so we've got like this right here. We've got 46 Pidgeys after 2 hours of playing, and then with red, I'll do 79 Pidgeys after 5 hours of playing. When you see numbers paired together like this number goes with this number, and this number goes with this number. They're a pair of numbers that go together. Some might call them an ordered pair. They're a point. So when they're giving you these numbers that go together, they've been stuck together permanently in this situation, which means that they're a point, a coordinate. So you can label it as such. We know that t is going to be our input, our independent variable, and that f of t is going to be our dependent variable. So we know that all of our points should be written as t f of t. So as such, we can write this information as an ordered pair, as a coordinate. 2 hours of playing means 46 Pidgeys. So careful here, t needs to be our x value. So we're going to write 246 times number of Pidgeys. We've also got 79 Pidgeys after 5 hours of playing, so we can write that as another point. So now I've written down a few things. I've got 2 points, and I've got a blank form of a linear equation, and we know that we want to write a function. And so we can use what we practiced on our previous page in order to know what we need to do next. What is the first thing that we need to do here? The first thing that we need to do, if we don't have one, is find the slope. You always need to find the slope. So in your prepare stage, you can say, oh, I don't have a slope yet. Well, okay, I need to find that. So you can write slope equals, and you can write the formula. y2 minus y1 over x2 minus x1. You can even go so far as to write question mark as a nice visual cue to you of like, oh, I need to solve for this at some point. This is like a list of things that you need to take care of. It's a nice visual cue. It gets rid of all of those words, and we're just focusing on the mathematical pieces that we can pull out of the words. Okay, so we first need to find our slope. In order to find our slope, we plug in these values. So now I'm going to start the actual solve portion of our problem. So I prepared first, and now I'm going to solve. First, I'm going to find my slope. So m equals 79 minus 46 over 5 minus 2. That should equal out to be 11, which is nice. Now that we have our slope, I'm going to go ahead and solve for my linear equation. My linear equation, y minus y1, it does not matter which one you choose. I'm going to go ahead and choose this one right here. So y minus 46 equals 11 times x minus 2. I'm going to isolate for y because it says that we do want it to be a function f of t, which means we're going to have like f of t equals something, which means we really want to isolate for y. Distributing my 11, adding 46 to both sides. 24. I'm going to rewrite it, so I've got f of t equals 11, not x, but t plus 24. All right, so we've now written a linear equation and we want to use this function to predict when Mr. Kaufman will have 300 Pidgeys in his inventory. So if we want to plug in 300, what are we going to plug 300 in for? T or F of T? We're going to be plugging in 300 for F of T. So you can even write in your prepare stage, T equals question mark when F of T equals 300. So that's like a nice, oh, I need to solve for T. So then my second step here is I need to solve for F of T equals 300. So 300 equals 11T plus 24. Go ahead and solve for T on your own. Solving for T to three significant figures is 25 point, and you got 0.090909, so that should be 25.1. Okay. Another way that we practice using linear, another accelerated way to be looking at linear equations and linear graphs is we're talking about piecewise functions. We're going to write a definition. In other words, we're going to write the equation that's represented on this piecewise function. I want you to take a second and analyze this graph. How many sections do we have in this graph? How many intervals do we have in this graph? How many different lines do we have in this graph? We have three different sections in this graph. You can see here at -3, a small change in behavior. So I might put in like a dotted line here to kind of show, like Frankenstein, we've taken a piece of one equation, we've ripped it out, and we've gone ahead and sewn it back into this graph along this dotted line. So here we've got one graph. After here, we've got a different graph, a different line, a different behavior being represented in the center. You can see right here. And then afterwards, we have a third and final equation, third and final line that's being represented over here. So this is the first time that we've seen this, that we have three separate definitions for this piecewise function. Remember with piecewise functions, oh, it says g of x equals, we've got curly brackets. I spent years in university doodling curly brackets. So if your curly brackets don't look like mine, you can always practice. And I'm going to define each of these in a row. I'm going to put my one equation here. I'm going to put my second equation here. I'm going to put my third equation here. You don't have to put in the lines. I'm just showing you what the plan is here. That we're going to have three separate definitions to represent all three different behaviors that are happening on the function. And we know that we're going to follow it with a domain of some kind. That we're going to have a definition that's an expression, and then we follow it with some sort of domain that says, okay, well, we're only looking at it between these two x values, between these two x values, between these two x values. We can even define our domain from the beginning. We know that the first domain here starts at this point because there's no arrow at the end, which means that that's where it starts. It does not continue on forever and ever. And it ends here. So for this interval, we're talking about between -9 and -3. So the domain for our first guy is -9 is less than or equal to x. And I'm going to say strictly less than -3. Realize that you can't include, you can't have an or equals to on two separate lines. So if I'm going to start with -3 down here, I'm going to include it in my domain, -3 to 1. And I'm going to say strictly less than 1 to talk about this guy right here, so then I can include 1 in the next one. This does not have to be the first thing that you do when you're writing linear equations. I just want to show you that it can be the first thing that you do. That we're talking about three separate domains, and so you can say, okay, well, the first domain, the second domain, the third domain. We've split it up into three separate sections. Now let's deal with each section and write the linear equation. We've got a line right here. If we were to extend this line, this idea of going up to over 3, we would realize the extension of it would hit at a y-intercept of -1. So for this one, we have a y-intercept of -1 and a slope of up to over 3. With that information, we can write the equation of this line. The equation of this line is y equals 2/3 x minus 1. We don't put y equals here, so sorry. It's just 2/3 x minus 1. So this is 2/3 x minus 1, and it's only being represented on the domain between -9 and -3. So that's all this is saying. Hey, we've got an equation, 2/3 x minus 1, and we only care about it between here and here. Okay, basta. Let's move on to the next one. I would like for you to tell me what the y-intercept and what the slope is for both of these guys, or for this equation right here. What's the slope and the y-intercept for this equation right here? The slope for this guy, m, is equal to up 1 over 1, up 1 over 1, so it's equal to 1. And your y-intercept is 0. In order to write that as an equation, that would be 1x plus 0. In other words, just x. That's it, just x. 1x plus 0, or just x. Okay, third and final one. I would like for you to tell me what the slope is of this guy. The slope for this line right here is we go down 1, 2, 3, 4 over 1. So the slope is -4 over 1. In other words, just -4. If we try and continue that slope going up, 1, 2, 3, 4, back 1, we can see that our y-intercept would have been 5. So continuing that line to see what's going on, it would have been 5. Knowing this information, I would like for you to write out the expression that is this line. If we have a slope of -4 and our y-intercept would have been +5, that would be -4x plus 5. We only care about -4x plus 5 on this domain. So this is how you write out equations of piecewise functions. We also talked about last lesson how to graph them. We'll go ahead and practice some more in class about graphing them as well as defining them. Good job today.